Here is for class 7 an example. This is problem 3, 122 out of Shigley, and it's for this eye bolt. It's loaded with 300 newtons. You can see that it's applied right here, and it's made out of a 6 millimeter wire that's got a radius, this inner radius of 10 millimeters from this center of curvature. And we want to estimate the stresses at the inner and outer surface at section AA. Notably, problem 123 is the same one, except that they are looking at section BB. So let's take a look at how we're going to approach this. So here we have the problem. And in many of our cases, the first thing we're going to do is do some geometry, right? So our geometry here, we were given some information in the problem, and they didn't necessarily care what our equations in our book were. So one of our first obstacles is to try to turn the information we were given into the variables that we're going to use that are right there, right? So one of the things that we want the inner radius. Well, they gave the inner radius as capital RI, right? So the inner radius that we want is actually the capital RI and is 10 millimeters. Another thing that we're going to want to have to get is RO. Well, they didn't give it to us, but they did give us the diameter. So the RO is actually going to be that capital RI plus their D, or it's going to be 10 plus 6, which we could do in our heads. And that's not meters, those are millimeters. And RC is something that we could calculate pretty easily. We could also look this up, by the way, in that table 3-4 for a circular cross section. But I think we could kind of gather from ourselves here that the center, right there, the centroid of that thing is going to be plus D over 2, and we could do that in our heads too, is 13 millimeters. The big R that we're gonna let's see, do I want to say that anywhere? Where do I use? Oh, I look up the equation for Rn now out of the thing, and Rn is equal to capital R squared divided by 2 RC minus square root RC squared minus capital R squared, right? And that's just a byproduct of them going ahead and doing the integration of that main equation where we had like A divided by the integral of dA over R, right? And they just did the increment. They figured it out and they did the calculus for us. So the big R, though, right there is actually equal to the diameter divided by 3. So capital R, well, right over here, is equal to 3 millimeters, which is really just the half of this diameter right there. So it could be confusing because they used capital R in this equation, but they gave this as a capital R there. Just keep those straight in your head. I'll write it out below this thing instead of trying to squeeze it over to the side. And so because everything's in millimeters, let's just leave it in millimeters. Later on, maybe we'll turn it into meters. I don't know. So that's just 13. Put that down. 13 minus the square root of 13 squared minus 3 squared. And I think that's everything there. I think so. And we get 12.825 millimeters is Rn. Notice that Rc is 13. So we got to be really careful here. And actually, we might want to go more sig figs than this. Because notice, we're going to subtract one from another. And when we get to E, like E is equal to RC minus RN. So we don't want to get them too close to each other, so when we subtract out, we only have a couple sig figs left. We want, if we can, maintain 4 sig figs with everything that we do. So here's an instance where rounding off is going to make a big difference, especially if I've seen many people do it, they get down to 1 sig fig. Remember, we're going to divide by E, or actually we should say we're going to divide by E. So if we only have 1 sig fig there, we could have a tremendous amount of error by rounding down. So here is I think when I did this right here, I think I did actually carry through more sig figs so that I had my 13 minus 12.825 and then some amount right here, because when I was done, I got 0.1754 millimeters. Right? That's pretty darn small right there, but we have to be careful because once again we're dividing by it. And by the way, if we wanted to check this thing up above, see this guy right up above, this 366, this would be the easiest one to check for, right? We say that I divided by RCA, and that's just pi over 64, and the diameter of 6/4 divided by RC, which is 13, and divided by area, which is probably actually would be something worth calculating, pi 6 squared. We get 0.1731 millimeters, which I said is a 1.35% difference. All right, so just to check, as a sanity check, right? Make sure we didn't go too far astray. Some other things we're going to need to have, we need CI is equal to Rn minus Ri, which ends up being 2.825 millimeters. CO is going to be, I'm going to call it the absolute value of Rn minus Ro, and that ends up being 3.175 millimeters. So that's the difference of the neutral axis to the inside and outside radius. That tells us, how far, if we were to do the regular MC over I, that's what that C would be, right? Now that's all geometry. We all do our geometry. Now let's do loads. And the best way to do a load is to do a free body diagram. So I'm going to draw right up, boom. And that didn't do the greatest job right there. Let's see if I can salvage this a little bit. Right, this is the section of interest right here. So that's where we draw the free body diagram, and we have a load that's applied right here that we say is 300 newtons. And we want to take the moment about the location of where the axial is going to be. The axial is going to be at the center, right? So we got the center right there. And we're going to get a reaction, and we'll say that's at A in the X direction. And we're going to have a moment. And if we're taking it about A, this guy is going counterclockwise, so this one is going to go clockwise. That's counterclockwise, Ted. Okay. Sorry. Talk to yourself? Yep, I do. And we'll say that we can call that M, and we call it MAZ if we want, right? It's the axis, it's going about the axis that's coming out of the page right there. And that distance is to the centroid is 13 millimeters right there. That's the one we use. So the sum of the moments about A in the Z direction is going to be 0 right there, and counterclockwise. And so we say that 300 newtons times 0.013 meters minus MA is equal to 0. So MA is equal to 3.900 Newton meters. Okay, and so now we need stresses. Now, I used a lot of paper on here, so I'm going to have to go onto an auxiliary sheet right here. But if we want to take the stresses that are going to be on the inside of this, we know that's going to be this is going to cause tension, right? You can see that causes tension, or we can see that causes tension. Either way that we want to do it. We also know that that's going to cause tension, so we know that F over A plus MCI over AE RI, and we needed that area, so we should probably have calculated that up here with our geometry somewhere, pi over 4, and that's going to be 0.006 squared. Did I get that right? 0.006 squared, and boom, 0.006 squared pi times 4 divided, and that ends up being 2.827, that's good enough, E minus 5 meters squared, right in there, okay? And so what we say is we have 300 divided by our 2.827 E minus 5, which, by the way, we calculate that out as a mid-step is a good thing to do, 10.61 megapascals. And then we add to there our moment, 3.900, and our CI, and so that's going to be 0.002825 divided by A, which was our 2.827 E minus 5, and our E, which remember was up here, 0.1754, but careful here. Okay, so by the way, that's the same thing as saying 1.754 E minus 4 meters, right? Might as well not go crazy with the decimal places, 1.754 E minus 4. And Ri, which was 10, right? So Ri, if you remember at the top, was 10 millimeters, or 0.01. We work through all of that, and we have the inside stress. The stress on the inside is going to be, so this comes out to, by the way, just as a means of comparison, 222.07 megapascals. So this is going to be 233 megapascals in tension is the answer that we get right here. So I'll go continue on a separate sheet here for the outside. And we have that same F over A, but now we have a minus MCO over AE RI. So we're going to have 10.61 megapascals. And then subtract out 3.900. The CO of this was 3.175. So we get 0.003175 divided by our area, which was our 2.825 E minus 5. And this is our E of 1.754 E minus 4. And I didn't leave myself enough room. That's going to be, remember, that's going to be RI, which was 16 millimeters. 16 millimeters. So that goes 0.016. And all of that comes out to negative 156. Right, so my outer stress is 145 megapascals compression, right? Because this is tension, that's compression is going to make that less, so it ends up being 145 megapascals. Now, we can check this by doing a finite element analysis of the thing. I have it already done. You can see right here that we found from here we get a negative 143, and here we get a 242, right? And you notice where I placed those onto there. I think I can do better, and if I have the time, at 15 minutes onto the thing, it's at 4:15 in the afternoon, I could go ahead and attempt to do this problem live here, right? So let's check them out. All right, so I have an FEA. I have my SolidWorks simulation ready to go. I'll start a new part, and hopefully everything will work out. Not seeing the screen I need, so I'm starting to think that perhaps this thing is messed up, but let's see. Maybe it will recover here in a second. Will you recover? All right, so I think my computer is going to be too slow to be able to do this today. When you know it, sometimes it's really a graphics thing with this computer. It does not like certain things, right? It doesn't like, sometimes it'll just wake up. Nope, it's not going to work. Okay, well, I wanted to be all special and that kind of thing, but apparently it's not going to happen. So anyway, you got to take my word for it. I'm not sure I want to do this example as a separate video. I could just talk through right now what the differences are going to be. It is a bit more complicated. I like it. I think it would be a good problem to assign, because it really kind of pushes whether you really understand what's taking place, instead of just going through the motions. You have to actually pick the thing apart, do a little bit of geometry, a little more challenged geometry. So let me just show it to you instead. So here's my solution to this. I don't know how I did this several years ago right here. So what the difference in the problem is that we're looking at this like little section. Let's see, let's go back to the original problem. So, where'd you go? Original problem, it's right here, and it's this transition that's making between this bend and this bend right here. So you have to kind of understand that that's going to be like a 45-degree angle. Did I get that? No, it's at a 30-degree angle. That's a little bit of challenge thing that you start out with. I messed up. I said, that must be a 45-degree angle, but it doesn't look like one. So you can start to pick it apart, and you can see that it's not a 45-degree angle. It's a 30-degree angle, it turns out. How do I know this? Because if you do a little bit of a sketch, you can see here's the inner radius, and here is the diameter. Here's the half the radius of the wire, and so we have this right here, and this. We could also see that we have this inner radius comes up to here. Here's the diameter of the wire, and then here is the inner radius, right? So if you pick that apart, you'll see that there's the inner radius, right? Because it goes, all that radius comes all the way up to there, and here's this inner radius, comes up to there, and there's the diameter in between. Tricky, huh? And here's 1/2 the diameter. And if you do that, you end up with 30 degrees. So that's what we've placed in there. So now when we go to do the free body diagram of this thing right here, for when it comes to tension, we want the force. This guy right here is going to be the force that causes tension right here. This force will cause shear. See, we're breaking this down into a component that's perpendicular to what I'm calling the X prime, and one that's right here coming across this way to the RBY prime, right? And then we also want to take a look at the moment that's taking place, and you can either do that by way of these forces, or, you know, I think that's probably the best way to go about it. So anyway, working through there, I was able to, working through this free body diagram, get what that reaction is going to be. It's 150 newtons. This is the one that's going to cause tension. This one we don't really care all that much about. But right here, what you could see is we could take the, so that's what I did, is I took this from the centroid of this thing, right? And I took, because I know that's going to be the distance right here, that distance to the centroid of that 13 millimeters, and I'll take the sine of 30, so that would be that distance right there. So that would be that would be the force would be coming around straight that way. It has to be equal to that, and so that would be what the moment is right here. So like almost nearly everything is the same. E, Ci, Co, they're all part of the same previous problem. So it's really, this one right here becomes a smaller value. Remember before it was like 10 point something or other. And this becomes smaller. So we get 116.3 megapascals in tension on the inner part. And we have a negative 72.71 right here. And transverse shear is 0 at that location. Am I correct there? Oh, at the I and the O. Okay. So these are okay. We don't need to do any kind of transformation. We don't need to do a more circle onto the thing. So these are the stresses that are being experienced. We have 116 and we have 72.7, and that's in compression. So let's check that with the FEA solution that I have in my slides. And I didn't, I said it's a minus 72. This is a minus 76. And I said this was 116, and it's 114. And I don't know how well I did with the, oh, and by the way, I aligned this with the section, I guess. I did align that with the section. But anyway, yeah, I'm not sure how well I did with the mesh, how fine of a mesh that I put in there. I probably could have got closer and closer to the results, but it's an interesting one. Okay, so I'll do one more example in the next movie and then call it quits for class 7.